because the de Broglie wavelength can be used, or the de Broglie wavelength equation, because it's a wavelength is equal to Planck's constant divided by mass and velocity. So if you know the mass and velocity of something, you can calculate its wavelength. It doesn't have to be an electron. Here, we're calculating the velocity of an electron that has this wavelength of 1.2 times 10 to the negative 10 meters. So we can arrange this real quick. We want the velocity equals Planck's constant divided by mass times wavelength. And so then we get 6.626 times 10 to the negative 34, which is Planck's constant, divided by 9.11 times 10 to the negative 31, which is the mass of an electron, and 1.2 times 10 to the negative 10, which would be the velocity. Oops. Or the wavelength. I swapped those. Wavelength. In meters. So then the velocity, if you type all of that incorrectly, which the first time I did this, I don't know, switch some numbers or something. You get 6.1 times 10 to the 6 meters per second. 100-ish times faster and be going the speed of light. Not quite. Not quite going that fast. But like I said, you can calculate the wavelength for not just quantum particles or things at the quantum level. You can also calculate the wavelength of regular sized things, which I don't know, I guess I'm a regular sized thing. This is my mass, 108.9 kilograms. Feel free to convert that into pounds if you want. And then the velocity that I was going on the bullet train. So what was my velocity while I was on, or what was my wavelength while I was on the bullet train? So we can use this equation without rearranging. Divide by the mass in kilograms. And velocity in meters per second. I don't remember what that one was. 626. My wavelength was 7.95 times 10 to the negative 38 meters. Which is interesting, right? Because it's a really short wavelength. Oh, did I calculate it? What'd you get? Times 10 to the negative 38? That sounds like maybe I transposed some numbers. Oh, I did 109.9 instead of 108.9. Basically the same thing. 8.03. Actually, I think this is related to the next question, right? So you can calculate a wavelength, but you don't see me oscillating. If you do, then maybe drink some water. You don't see the wavelength of objects that are at the macro scale, at our scale of things, because the wavelength is way smaller than our size. When we calculate the wavelength of here it's an electron with a wavelength about that of a chemical bond, that wavelength is about the size of that electron. So they're on the same scale, and so it's significant. But yeah, I don't know. I remember the de Broglie wavelength for this reason, that you could just throw some numbers at it, say how fast would I have to go to have a wavelength approximately equal to my size. We're not going to do the math now, but we can do the math later. If you remind me, I'll do it in lab. Okay, quantum mechanical theory is universal. And I think I brought this up at the beginning of this chapter, that these weird properties of subatomic particles are the particles that make up everything. So why is it that we have a distinction between these subatomic particles, which can have wave-like and particle-like properties, but they don't apply to everything else? So this thrown baseball should exhibit wave properties, but why don't we observe that for that baseball? Why don't we see the wave, the baseball act like a wave? It's not B, because for B, baseballs don't have any charge. That doesn't really matter. Quantum mechanics apply to neutrons, which don't have any charge. Quantum mechanics, again, applies to everything. It's universal. The reason it doesn't apply to baseballs, though, is the same reason it doesn't apply to me, that the wavelength is so small, it's minuscule compared to the size of the baseball, or minuscule compared to the size of me, of a person. Okay, so we skipped over that. We talked about the uncertainty principle, wave-like properties. I think I need to better define this complementary. Because we think about complementary as things that go together, complementary colors. I don't know, you could do the whole color wheel. I don't have it memorized, but there's certain colors that you want to mix, certain colors you don't want to mix because they're complementary. They look good. So I think when we hear this word, we think of that. Oh, these two things should go together. But really what complementary means here is this: the more you know about one property, the less you know about the other property. So we can observe electrons acting like particles, but then we won't observe them acting like waves. We can observe electrons acting like waves, but then we won't see them act like particles. So they're independent in terms of measurement, which was the whole experiment, the uncertainty principle experiment, where you shoot electrons through a slit. Even if you're shooting one electron at a time, you eventually end up with an interference pattern. You don't see bright spots, just two bright spots, where the electron particle would be going through one slit or the other slit. But when you set up another experiment to see which slit is that electron going through, you'll only getting it lighting up at one slit or the other. And if you're shooting one electron at a time, you'll never see it light up at both slits at the same time. And it's just really weird, because until it's observed, it can be in two states at the same time. So if we observe it at the slit, we collapse it down into it only does one or it does the other. If we observe it later after the slit, then it goes through both and interferes with itself, and you get an interference pattern. So I went over the Heisenberg uncertainty principle. Again, just like wave-like and particle-like properties are complementary, speed and velocity of an electron, speed and velocity are almost the same thing. Position and velocity are complementary. We can know an electron's position or we can know its velocity, but you can't know both at the same time. So you get some weird stuff out of this, like determinacy, indeterminacy. We saw this. This is the deterministic trajectory of a baseball. Baseball gets thrown, it will fly along a path. It will land where it lands depending on drag and how much energy it has, how high it's thrown, all those kinds of things. Electrons don't do that. If you could launch an electron from point A towards point B, it'll end up in different places and taking different paths to get there, if you can even think about it as taking paths. So again, because position and velocity are complementary for an electron, energy and position are also complementary, so we can know the energy of it, or we can know the position. This is all quantum mechanics, so it is all weird. So the orbitals that we're going to talk about next come out of Schrodinger's equation, which calculates the probability of finding an electron at some distance from the nucleus. And more specifically, we're going to be looking at phi squared. That's phi? Phi? Psi. Thank you. Psi squared. So we can plot psi squared, then that represents an orbital, and it gives us this sort of three-dimensional probability of finding it. And again, this is all just coming out of Schrodinger's equation. There are these numbers, these quantum numbers, that define different properties of the probability function for finding an electron. And we can break this down and make it maybe a little bit more intuitive by saying that the principal quantum number defines the energy. The angular momentum quantum number defines the shape. And then the magnetic quantum number defines the orientation of that shape. or you can almost think of it as like the position or positioning of that shape around the nucleus. The fourth quantum number, the spin quantum number, I suppose you can think of as phase. But there's only upspin and downspin, or positive 1/2, negative 1/2, but they're not actually spinning. Okay, the principal quantum number just represents the energy of an electron. And for hydrogen, we can say this is basically the Rydberg equation, but instead of for a difference in energy or a change in energy level, we're just saying for any energy level. So the energy of that principal quantum number is going to be this negative 2.18 times 10 to the negative 18 times 1 over n squared. And then the energy is negative here because the energy of an electron closer to a nucleus is less than the energy of an electron away from the nucleus. So it gets stabilized as it gets closer to the nucleus, meaning it has lower energy. So this is what you used or will use when you're calculating, or actually you'll be calculating this value in kilojoules per mole for the lab for changes in energy levels. So these integers, they go 1, 2, 3, 4, and so on. But the energy of each level, which told by the factor of 1 over n squared, the difference in the energy of each level gets less and less as you get farther away from the nucleus. And that kind of makes sense because down here at n equals 1, that's 1 divided by 1 squared, which is 1 over 1. At n equals 2, that's 1 over 4. So it's 1/4 of the energy at n equals 1. At n equals 3, that's 1 over 1/9, so that's 1/9 of the energy, and then 1/16 of the energy. So for every energy level, the difference between it and the previous energy level gets smaller and smaller by 1 over the squared. All right, the angular momentum quantum number, or L, corresponds to the shape. So L equals 0 is the S, which is the sphere. L equals 1 is the dumbbell, p orbitals. D is like a cross, 2 dumbbells crossing. Actually, I don't remember what the f orbitals look like. It's been a long time since I've drawn them. There's one d orbital that has a donut shape you might be thinking of. And we could have not any of these orbitals or any of these shapes at any energy level. There are certain ones that are allowed, certain ones that aren't. We'll get into that later. But then the type of orbital, the shape of the orbital is defined by this L, angular momentum quantum number. Yeah, okay. So the L can have integer values from 0 to n minus 1. So that means that if I plug in my principal quantum number for n, so at n equals 1, then the angular momentum quantum numbers that I can have are going to be 1 minus 1, which would be 0. So at n equals 1, we can have L equals 0. At n equals 2, I can have L equals 0 and 1. So then at n equals 3, what are the possible values of L? So all of the possible values, because 0 is possible, but not just 0. 0 and 1 are both possible, but again, not just 0 and 1. Because at n equals 3, 3 minus 1 equals 2. So I can have L equals 0, 1, and 2. Mm-hmm. N? Correct. Cannot be a negative number. positive integers only. N can be positive, L can be, or I should say, N has to be positive, L has to be positive. The magnetic quantum number, like I said, this is the orientation of the orbital. And for each of these, M sub L can equal negative L, positive L. So if L is 0, what would be my possible M sub L's? Negative 0 to positive 0, which there's not such a thing as negative 0 or positive 0, so the only one available is 0. And so if we apply that to a sphere, remember L equals 0 is an s orbital. So that's a sphere. If I rotate that sphere, or if I turn it and face it a different direction, is that a different orientation? No, because if I rotate it or do anything to it, those are all the same. So for a sphere, there's only one orientation possible. If L equals 1, what are the possible M sub L's? Yeah, the integers from negative 1 to positive 1. So negative 1, 0, positive 1. I know we haven't quite covered this yet, but some of you will have to dig back to Chem 20. Right? So the L equals 1 is a p orbital, which has the dumbbell shape. And there are 3 p orbitals. And they're arranged or oriented on 3 different axes. So one of them would be p sub x, which is on the x-axis. You'd have p sub y. You'd have p sub z. And so each of these magnetic quantum numbers is referring to one of these orientations of the p orbital. Off the top of my head, I don't remember what convention there is, because it's got to all be based off of something since there's perspective involved. But I guess since they all exist at the same time. So there's 3 possible orientations of p orbitals. And the same thing if I go L equals 2, those are the d orbitals, and there's 5 different d orbitals. Going from M sub L is negative 2, negative 1, 0, 1, 2. Good, so just did this one. D. So if you know it's L equals 2, then you know to go from negative 1, negative 2, negative 1, 0, 1, 2. It's D. And again, these are, I'm going to do my best because they're in between. Each of the d orbitals is on a different plane. And then there's the one that's shaped like a donut, and there's one that's on the axes. And this one would be, so this would be dxz, dyz, dxy, dx squared minus y squared. And then, oh, I don't remember what that one is. Oh, z squared. So there's 5 different orbitals. So negative 2 through positive 2, all those integers. Each one of those is a different orientation of those d orbitals. So no, you should be able to recognize them. So if I drew one, you should be able to say that's a d orbital. You don't need to memorize these. Like that the x squared minus y squared is on those axes. But if I showed you an orbital that looked like this, you should know that's a d orbital. Or if I showed you this one, you should know it's a d orbital. And that these would be p orbitals, s orbital's just a sphere. There are much better pictures in the book. Okay, so the last one is the spin quantum number, and in my opinion, this is the easiest one because it can be either positive 1/2 or negative 1/2. And you can have a positive 1/2 and a negative 1/2 for every m sub L. So for each orbital, you can have 2 electrons in it, and one's positive 1/2, one's negative 1/2. Yeah, all electrons have the same amount of spin, the orientation, which direction they're spinning, quote unquote spinning. It's a property that's just described as spin because sometimes it works like spin, but other times it doesn't. Just remember m sub s, the s is for spin. Okay, so whenever you're describing any orbital with these quantum numbers, each set of numbers describes a different orbital. So orbitals with the same value of n are at the same principal level or at the same sort of overall energy level. Then orbitals with the same values of n and l are said to be in the same sub-level or subshell. So if we did n equals 2, L equals 1, m sub L equals negative 1, each of these sets of numbers describes a different orbital. And then because they're both in n equals 2 and L equals 1, we'd say they're both in the same subshell. What would be the last orbital in that subshell? So to be in the same subshell, it's got to be n equals 2, L equals 1, and then m sub L. Because L equals 1, that means I can have negative 1, 0, and positive 1. So those 3 sets of quantum numbers describe all of the 2p orbitals. Any questions so far? Okay. So those are all the quantum numbers. In general, the number of sublevels within a level equals n. So n equals 1, there's 1 sublevel. N equals 2, there's 2 sublevels. N equals 3, there's 3 sublevels. And so n equals 4, there's also 4 sublevels. And then you can take these and define sort of equations to say how many of orbitals within a sublevel there are, plus 1. So if I put in 0, L equals 0, then I've only got 1, because 2 times 0 would be 0, plus 1 is just 1. For p orbitals, you've got 3. D orbitals, there's 5. Okay, so list the quantum numbers associated with all of the 5D orbitals. Take a minute. Try and write those out. All right, so what's my first quantum number? It is 5. So n equals 5. What's the letter of the next quantum number? L. And what would L be here? 2. Then m sub L, what would all the possible numbers be? Negative 2, negative 1, 0, 1, 2. And what about m sub S? And negative 1/2. Let's do the negative first. Negative 1/2 and positive 1/2. So I think the easiest one here to do is n, because this number here, the 5D, the 5 is n. So n can be just in general 1, 2, 3, so on. The L's now depend on which letter designation orbital we're talking about. So we've got S, P, and D. So if L, say if the letter S, P, D, F, the L would be 0, 1, 2, 3. And then for each of those, we're going to have m sub L. For S is going to be 0. For P, it's negative 1, 0, positive 1. For D, it's -2, -1, 0, +1, +2, -3, -2, -1, 0, 1, 2, 3. And for each of those, +1/2, -1/2. Yeah. Oh. Yeah, that'd be fine. If you show notation that it's, yeah, if you use math notation to say it's all of the integers between, the set including, that would also work. So I think like the ones to remember, or to at least very much remember how it works, is the L's. And it's SPD, and you just start from 0, 0, 1, 2, 3. Then for M sub L, you can have negative to positive, whatever L is, including 0. That's part of why we always get odd numbers for the number of orbitals. S is always going to be 1, 3, 5, 7. And then positive 1/2 or negative 1/2. So I guess I should ask the question, how many 5D orbitals exist? Be 5. Because these tell us the energy level and the shape. N equals 5, L equals 2. Because we're talking about basically the 5th principal quantum shell. L tells us we're talking about the d orbitals at that shell. Now the d orbitals are all of these M sub L's. So each one of these represents a different d orbital. How many electrons can I have in my 5d orbitals? How many total electrons if I filled up all of the 5d orbitals? 10. Because every electron, I guess maybe we haven't quite covered this, these will describe all the way up to which orbital we're in, and then the M sub s is the spin of the electron in that orbital. So to have unique quantum numbers, I could have n equals 5, L equals 2, M sub L equals -2, and then M sub s is positive 1/2. All those same numbers, M sub L equals -1/2. So that's 2 in this -2. And then I could do the same thing, but -1, positive 1/2, -1/2. Yeah.
So would it ever just be like positive 1/2 or like just -1/2 for the spin?
What do you mean?
Is it always going to be -1/2 and +1/2 for the spin of the electron?
It can be one or the other.
Okay.
Can't be both. So if I was to write out the principal, or the principal quantum numbers for one of my d orbital electrons, I might write n equals 5, L equals 2, M sub L equals 0, M sub S equals positive 1/2.
Okay.
And then if I change this positive 1/2 to -1/2, that's a different electron in the same orbital.
Gotcha.
If I change this to positive 1, let's say, that's an electron in a different orbital.
Okay.
But it's still in a d orbital. I don't think that ends up being important in this class. Most of the questions are, is this an allowed set of quantum numbers? So usually that involves saying, so here we've got n equals 5. So L, what would be my possible L values? Huh? Yeah, so n equals 5, I can have n minus 1 angular momentum numbers. And that means I could have 0, 1, 2, 3, and 4. Actually, it's maybe a good tie into this next one. So we've got sets of quantum numbers. Each one is supposed to specify an orbital, but each one of them has a mistake, something that's not allowed. So we want to replace the values that aren't allowed with one that is allowed. If you look at A, yeah, or it could be, I guess in this case, with only changing one number, L can only be one other number. So it's this one that's wrong, and that can be 2. Why can't it be 1? Yeah, m sub L here is plus 2. So I can make L equal to 2 because of my possible m sub L values are -2, -1, 0, 1, 2. So positive 2 is allowed with L of 2. Okay, how about B? Now, are there other values that I could change? So the problem here is m sub L. Because L equals 1, that means I can only have -1, 0, or positive 1. Or if we changed, actually, no, you'd have to change n to 3, L to 2, and then m sub L equals -2 would be okay. But we just want to change one number. So this could be 0. It could also be -1 or positive 1. Because those are all allowed m sub L numbers when L equals 1. And what's wrong with the last one? There's actually 2 ways we could change this last one. Yeah, so we can either the N or the L is wrong here. So one solution would be to take L, make that 0. Or we could say N equals 2, L equals 1, M sub L equals 0. So maybe another way you could think about this is that each quantum number tells you what the allowed quantum numbers are after it. So if N equals 3, then I can have L could be 0, 1, or 2 because N equals 3. If L is 2, then it tells me that M sub L can be -2, -1, 0, 1, and 2. All right. Oh yeah, we talked about electronic spectroscopy. Should have taken these out. Okay. This is the next thing I want to talk about, probability density. All right, so we got all those quantum numbers. They all come out of Schrodinger's equation. The other thing Schrodinger's equation gives us, essentially, is that for each of those sets of quantum numbers, it describes a probability density of those orbitals. So the probability density is specifically the probability divided by the unit volume. So if you've got a really large volume, it dilutes the probability. If you've got a really small volume, it means that there's a really high probability in that one area, or I guess it dilutes psi squared. So for an s orbital, it's spherical, and the probability density decreases as the distance from the nucleus increases because the volume gets larger and larger, less and less of a chance as you move away. So plots will represent this like multiple exposure photograph. The thing to remember is the electron is not moving around the nucleus like a moth around a flame. So it's not just like moving in straight lines around it. In one sense, the location is spread out over all of that probability density region. And it can, even in rare circumstances, be in 2 places at the same time. It's quantum superposition. So often you see them like this. Got all of these dots, and it's like taking a bunch of different pictures. If we were to stop the particle and have it be in one spot at a time, after a ton of different pictures, you'd see something like this fuzzy sphere on the left. The problem with this is, like the slide says, it implies that there's a really high chance of finding the electron at the nucleus. It's not actually the case. It's not ever going to be at the nucleus. So just the probability density curve looks like this, where when you're really close to the center, it's really high, and then the probability decreases as you move farther out, because we're starting to use larger and larger volumes. So instead, we use a radial distribution function. So this is the total probability. So if we added up all the probabilities for a certain distance from the nucleus, so if you think of a shell, we take all of the probability of finding it on that shell, That's the total probability, and that's the radial distribution function. And so we're taking the whole sphere and we're collapsing it down into a single line. And then we're saying, for each distance, what's the total probability? And this kind of solves this issue of looking like at the center or at the nucleus, there's a high probability. Because what happens when you're at the nucleus, the volume of the thin shell of the nucleus is 0. And so the probability of finding it there is also 0. And then it increases as you go out, it maximizes at some distance, and then it goes back down again. So you can see that in this plot. So here we're throwing out all of the whole sphere. We've collapsed everything down so that we can look at it in terms of just distance as you move away from the nucleus. So probability at 0 is 0. There's no chance that you'll find the electron at the nucleus. For this 1s orbital, it is the closest one to the nucleus. So as we move out, it peaks at 52.9 picometers. Which is also the radius that Bohr had predicted, which is cool. Even though he had the wrong idea, he was able to predict that the most likely place to find it is at 52.9 picometers. Okay. Now, as we move out, we get other spherical orbitals, but then we get nodes. The node depends on the type of orbital and the principal shell number. So you can think of it like a string, where we've got this string oscillating in a standing wave. And we have these nodes where basically the string's not moving at all from some center point. It's like that. And that's what you see actually in this image, which is from a YouTube video. Minute Physics, I think, is the channel. I can scroll down. Yeah, it's at the top left. Minute Physics. Cool video. So this would be like the 1s orbital down here in the blue. And then green would be 2s, 3s, 4s. And so you can see, it's maybe a little hard. Can I actually zoom this? See that there's a spot where it gets a little bit darker in the center. That's where the nucleus is. That's where the probability drops to 0. And then in our 2s orbital, this adds a radial node. So you see, we do have some chance of finding it in the middle-ish here. And then basically probability drops to 0, and then probability goes back up again. And so we get almost these blank shells inside of where we could find this nucleus. Or we could find, sorry, this electron. And actually, wait, we could play this a little.
Electrons with more energy are more likely to be far away from the nucleus. The motion of the dots is showing the flow.
So we can have these places where, and on our radial distribution graphs, functions, this is another view. I don't like this one as much, but there's a lighter spot here, which represents where this radial probability drops to 0. You can zoom in on those, and these are lined up. So probability density and total radial probability both drop to 0 at these points. It might be a result, if you saw the higher resolution, better picture of those, it looks better. It looks not like dark like a higher density, it looks empty because there's none of the little spheres there. So you can see that for 2s, we added 1 node. For 3s, you add 2 nodes. And then we could also use these down here to say, like, where is the electron most likely to be? And that's just going to be the highest point on these graphs. So for this one's the 2s, this is the 3s. For 2s, it's, you can actually draw perfectly straight lines. Software, so it's, I don't know, 2.800 picometers, so 280. And for 3s, we would draw a point down from here, and it's about 680. So you'll have nodes like that. Oh, I should say, it wasn't in here. These are, really belongs up here. Or here? These are radial nodes. So one type of node, these are the ones that sort of occur as these like spheres inside the sphere where the probability is 0. Okay, so our s orbitals, again, Angular momentum quantum number also represents this s orbital. Two ways of talking about the same thing. Basically, each principal energy level has one s orbital, right? N equals 1 has 1, n equals 2 has 1, n equals 3 has 1. There's never more than one s orbital. And for each principal energy state, that's also going to be the lowest energy orbital. Basically spheres. And then the number of nodes, radial nodes, which is the only kind that s orbitals have, is going to be n minus 1. So n, again, being the principal quantum number. So our s orbital at n equals 1 will have 0 nodes. Principal quantum, or at n equals 2, we'll have 2 nodes. N equals 3, we'll have 3 nodes. For p orbitals, again, L equals 1. We've got these 3 different axes. We've got the 2 lobed, so it's that dumbbell shape, or sideways balloons. Has 1 node at the nucleus and a total of n nodes. It has 1, I guess here it has 0 radial nodes. It has 1. No, it'll have radial nodes, but it's a total of n nodes. So at n equals 2, it has 2 nodes. Huh? No, it assumes 1 radial node and 1. Let's look at the simulation. Where'd it go? Let's take a look. This is the simulation I'll be looking at in the lab. So P. Because that looks like... Oh, maybe it's including all of these? Should have 2 nodes. Let me go to n equals 3. So that's a... What was the other node? It's got 1 radial node. Well, angular node. Thank you. 1 radial, 1 angular. It must be 2. I don't think the book talks that much more about it. Or it'll come back. So the thing that maybe is a little bit deceptive about the radial distribution function for these is that it looks like it would for, sorry, still thinking about nodes, like it would for a 1s or a 2s, an s orbital, where it goes up, then it comes back down. But it also has all of these, it's got these 3 different orbitals, and I think that's where the angular node is. But the distance is going to be at the thickest part of these nodes. Whether or not it's in it's in the x or the y or the z along the lobe. So if we move out from the center going this way, that's where we're moving from here out and away, and then it drops off. So d orbitals then, each principal energy state above n equals 2. It's got 5 d orbitals. X, y, x, z, y, z, x squared minus y squared, and z squared. These 4 all look roughly the same. They have 4 lobes. The only one that has 2 lobes is the dz squared. So at principal level, higher principal levels, then we'll have even more nodes. So those are the 4. This one is the one that always trips me out because that donut does not touch this sort of what would look like a P-shaped orbital lobe. And the electron can go from the dumbbell part to the donut part and back without ever crossing the distance in between. So it can move, can't really think of it as moving from one point to another. It exists in one point and then is in the other point without crossing the points in between. Kind of. But it's also the fact that it's a wave, and in some ways like a standing wave, otherwise not. F orbitals, there's 7 F orbitals, mainly 8-lobed. Some of them are 2-lobed with a toroid, and the orbitals just get weirder and weirder. Ah, yes. Now I remember. So these are pointing out in between axes for the most part. Be very hard to draw. So is the f orbitals. Again, these are mathematical wave functions. So they are just calculated. And for each of these wave functions, you can have a positive or a negative value. Or you can have nodes where the wave function equals 0. And so the sign of the wave function, whether it's positive or negative, is called its phase. So either orbitals are interacting, where their functions are in phase, or they can interact and be out of phase. Talk more about that later. But when things react, it's these orbitals being either in phase or out of phase, and then the way that they interact and construct new wave functions, and energy levels change. So you can think of orbitals at phases, again, using a standing wave. So this would be going up and down, and while it's up, we maybe say it's positive. While it's down, we say it's negative. For a 2p orbital, we've got a different phase for either side of the p orbital. So one side's positive, the other side's negative, and then it switches. And actually that you can see in this simulation. You're not crazy, it has changed colors. If I turn up the simulation speed, you can see the phases changing and alternating. And you go real fast. Okay. Oh, good, this is the last slide. Why are atoms spherical? We depict them as spherical because if you take all of these orbitals, they all stack up on top of each other to essentially be a sphere. And you can also think of like, why do the orbitals get weirder and more complex? Well, because if you have just an s orbital, like the lowest energy level, there's 2 electrons max. It's really efficient to just fill that whole space with one sphere. But as we start to add more and more electrons, and these principal shells get larger and larger, there's more space that can be filled. And so these smaller and smaller gaps get filled by d orbitals and f orbitals, but they are trying to squeeze into all of the cracks. Because they reduce their energy when they get around a nucleus. Oh, we actually have time.